solving the heat equation. So actually you can solve other equations, just really important equations like wave equation, heat equation, and Laplace equation. So the most important equations you can solve it in the whole real line using the Fourier transform. Of course, not always it's going to work, but depends of your conditions. You'll have to use other techniques. But it's just amazing that with Fourier transform you can solve all these three. Those are the three main equations that you learn in differential equations.
So we're doing it in one dimension? Or?
One dimension, yeah. So, but this argument can be extended to several dimensions. So we take the heat equation. So, well, you know, we have two variables, right? We have uxx and xt. We have ux0 equals f of x. So taking Fourier transform on both sides. So we take Fourier transform of the small ut, and then we take the Fourier transform of the usx, right? And then I should say Fourier transform with respect to x. Okay, so we are basically we are going to integrate with respect to x. Okay, because you could take Fourier transform with respect to time, but we are not going to do that. So that means when you take the Fourier transform, you are saying I'm going to kill. You are taking the Fourier transform with respect to x. You are killing the x, so you are going to get a constant. So that's what I like to put k. Okay, so I'm going to, instead of, last time I was using this notation for the frequency, so today I'm going to use k. To means I'm killing the x and making it a constant. So basically it's like you choose a frequency. Okay, so you take Fourier transform and then you take the Fourier transform or the initial data, the ux0 and the Fourier transform of the f of x. Okay, so I just took Fourier transform of everything over here. But since last class we learned a couple of things, right? So we learned that, let me show you here, last class we used we proved that, so I want to show you so you don't think I'm lying. So here, we proved that the Fourier transform of the derivative with respect to time is the derivative with respect to time of the big U of the Fourier transform, right? But today I'm not going to use this one, I'm going to use k. So for last class I'm going to replace the derivative with respect to time by the U with respect to time, the capital U. And also, you know, I take the Fourier transform of ux0 and I got u psi 0. Today I'm going to use uk0 because I want to say that's a constant. Okay, so this is in my when my variable is t, any variable is constant, k or zeta or call it whatever. But now I'm just going to work with t's, right? So I got this one from last time. Also the second derivative with respect to time, you can take it out, but I don't have second derivative. So I took first derivative and then we took second derivative, and then for second derivative I have this formula that was last time. I'm going to use it today. So using all those properties over here, this one using properties from last class, we get this guy becomes capital U, derivative with respect to time. I just like to use that notation, kt. Okay, so my x disappears and becomes k. Oh, last time I used this one, but today I'm gonna use k. And then equals, and this is the last formula was ik square ukt, and this is just minus k square ukt. Okay, that was from last class, last time. Sorry, this is what I'm doing. Sorry. Well, it's true. So this one is that one, and this one is this one. Okay. So, and this guy for last class becomes uk0 equals, and then I use the Fourier transform of f of x. I just call it capital F of k. Okay. So I have ut equals minus k squared capital U, and then I have uk0 equals f of k. So this is just as first order ODE, and we know I solved it last time, remember? So my solution looks like using my ordinary differential equations. My solution is gonna look like capital UKT equals f of k e to the minus k squared t. So far I haven't done anything today, so I just recall all that we did last time. So now, remember I make you a drawing. Remember I make you a diagram reviewing all the steps. So today we have to go for the last part of the box. So far what we have done, check, take Fourier transform, solve it with using UDEs. Now we have to go back. We are here. I have to go back. So today I'm going to have to use my theorem of convolution and my Fourier theorem inverse. My Fourier inverse theorem. So this is one. I have my Fourier inversion theorem just says that if I take the Fourier inverse of the Fourier transform, it just gets the same function except for a set on measure 0. So basically what you recall from that is, so just I'm gonna get my same function back, okay? And the other one is this. The Fourier transform of a convolution is the product of the Fourier transform, or saying in another way, the Fourier inverse of the product of the Fourier transform is the convolution of the original ones. So that's the one that I'm gonna need. Okay. So so let's take Fourier transform inverse. Taking Fourier transform inverse. So that will be Fourier transform inverse of U kt and Fourier transform inverse of fk e to the minus k squared t. Okay, and then here your variable is k. Okay, that means we want to recover x. Okay, so by the inverse Fourier transform, U is the Fourier transform of small u. So the Fourier inverse of the Fourier transform of small u, well, they kind of cancel each other, right? But they don't really cancel. They just, but we recover uxt almost everywhere by a set of by a set for a set of measure 0. But that the two of these are equal except in a set of measure 0. Now this part, the Fourier inverse of fk times e minus k squared t. So for this part, I have fk times e minus k squared t. So I need to do a little homework. This is g of t. Okay? That's g of t. Or capital G of t. I need to find a small g of t. So the question is, who is a small g of t? So g of t is the Fourier transform of a small g. So the question is, who is the small g? Okay, but using the convolution theorem that we don't have time to prove, but we can use it. By this, the Fourier inverse of the product, what is it? You guys remember? What is the Fourier inverse of the product by the convolution theorem? The convolution of little f and little g. Okay? And that will be your solution. Okay? That will be your solution. But so we could say finish there, but we can do better than that. So we can find g. Okay? So who is g? So we need to solve this integral. We need to solve, in order to find g, small g, we need to find the Fourier transform inverse of g of t. Okay, and the Fourier transform inverse of g of t is 1 square root of 2 over pi minus infinity to infinity, and the difference here is that e to the I kx, instead of being e to the minus I kx, you have e to the positive I kx, because it's the inverse Fourier transform of the g of gt. But who is gt? Gt is e to the minus k squared t, and this is dx. So we need to find that integral, or this looks like 1 over square root of 2 pi integral of e to the I. So if we factor I, that will be I kx plus I k squared t dx. Agree? So I just factor I, and that's the way my integral looks. So we will need a famous formula from real complex analysis, or from complex analysis, complex variables. So this is one of the standard formulas you prove in complex analysis. Okay, but I'm gonna give it to you. So lucky for us, we have a formula from complex analysis. So we don't have to prove it, but make sure when you take complex analysis to make sure because you do your Cauchy-Riemann integration, and it's very nice, the proof. So the formula is the following. So let me put it on red. It's minus infinity to infinity e I a k squared plus 2bk dk. Oh, sorry, here is not x, it's k, because I want to get, so you see, I want to disappear k and hold x and t's. Okay, so that's the rule. If I integrate with respect to k, k disappears. So I need x and t's because I need my original function. So here, this has this really nice formula. Square root of pi I a e to the minus I b squared over a. I love this formula because my first paper was using this formula, so it simplifies things a lot. So this, now we can use it here. Okay, so we want to solve, we want to solve this equation, this integral, using this formula. Okay, so in order to things work, so taking a, what is a? If you compare these guys with these guys, what is a? IT, really good. And then what is b? Say again? No. X over 2. There you go. So x over 2. So now we just apply this formula here, and we got a nice formula. So we have 1 over square root of 2 pi, and then I got a square root of pi I a is it. This is beautiful. My I cancel. Then you have e minus I b squared. What is b squared? X over 4, x over square over 4. And what is a? It. So you see, the i's go away. So I have finally this. They have. We can leave it like this: a square root of pi over 2 pi, right? And then you have e to the minus x squared over 4t. That is g of t. Sorry, g of x. That's g of x. So I have found my g of x, because f inverse of not g of t, sorry, g of k. Sorry guys. So because is on k, not t. Okay. So so now, and here f my solution is uxt of f convolution g. That's my solution. So finally, that's my solution. Finally, we have solved a problem that took 1,600 years to solve. Well, more than that, right? Because Fourier solved it by the 17th century. Yeah. So that's so so f convolution. So uxt equal f convolution g, and this is the integral So I'm gonna write it like f of y dy, and this is g x minus y, but in my notation everything has a square root of 2 pi. Okay, so that's my notation. So in my notation, convolution, Fourier inverse, and Fourier, everything has 1 over the square root of 2 pi. So now I go and I write 1 over square root of 2 pi, and g, my g is, I can write it here. So, oh sorry, sorry guys, I missed here. P cancel, and then I have 2t, right? So I have, were you correcting that? So I have really 1 over the square root of 2t, right? That's what yeah, I finished with that one. Okay, so how that, what that remember, what doesn't remember you, Lee? What this look like? You're a statistician, right? You don't remember? So what about we put it like this? Sigma and sigma. The normal distribution, yeah. So t, for t, as for us, for partial differential equation is time. For statisticians is a standard deviation. Okay. It's a very important formula. And if you guys, so Gamma went to the defense of Jose, right? So he shows that he was talking about random walks and how communications, when you are using Twitter or Facebook, this is a random walk. So you don't really know if I tweet. Suppose I send a tweet, or I put a tweet in my account, right? So somehow Gamma emailed me saying that he got my Twitter. So how he got my Twitter? Who knows? Somebody probably, I sent it to a friend, and that friend got it to, or that friend got it from me, and then started sending it, and finally Gamma got it. So it's totally random walk. So that kind of random walk is, it has, when you make an approximation, looks like the heat equation. It's the heat equation. So now G is gonna be e to the minus, evaluated x minus y. X minus y squared over 4t and divided by square root of 2t, and then f of y dy, and this is, you multiply these guys, so you got 1 over square root of 4 pi t, then you got e to the minus x minus y squared 4t f of y dy. Okay, and that's it. That's your solution for the heat equation. Okay, so that's really great that we can figure out that. And you know, this formula, this integral, is basically what you need for I will make one for your exam. It's like you will just use the same equation, the same integral. Why do I call it what? Heat? Oh, because Fourier establishes, so there is a derivation, so you can look on the Wikipedia. So they make a derivation of the heat equation. So it's like there is a law of heat transfer. So you start like that. So there is a law of heat transfer, how things transfer heat. So you start writing it, and then you start finding limits, and then you finish with this. So there is a derivation. Just go to Wikipedia. So you will see they start with the heat transfer law, and I think that was designed by Fourier too. So it's the same thing. For example, in at least that one has. Schrödinger equation is more difficult to derive. It's more because you have a complex variable. So okay, guys. So that was one objective. So I presented you the one real application and how do you use this Fourier transform, this convolution. And then don't forget that I show you a theorem that is one of the theorems you prove in partial differential equations, that the solution of the heat equation looks like that. That's what we proved today. But also you have by dominated convergence theorem you can prove that this guy is going to converge to the initial data. Well, here I choose f of y, so I put it here g, but so to be consistent f, it doesn't matter, but to be consistent today we talk about f. So and then you have stability, so that's pretty typical class of PDEs. So you have 15% of a PDE class here already. So now we're gonna do another theorem I want to prove, is the corollary, and it's when we interchange derivative with respect to time with the integral. Okay, so this is another corollary from dominated convergence theorem. Corollary of dominated convergence theorem. So suppose that for some t sub 0 in AB, the function x to f of x t sub 0 is integrable on x, so or the real line. So let's put just real line. So that's first assumption. Second assumption, I suppose. Second assumption, suppose also that the derivative with respect to f with respect to time exists on the real line and cross an interval. So we're just gonna justify that when you have xt function. So you'll understand better in a second. And that there exists an integrable function g on x such that derivative with respect to f with respect to time xt is less or equal to g of x. Okay, so you see I assuming that my f is two variables function. Okay, so my f is a two variable function, and this is the other parts are kind of, you know, like to everything is properly defined, but basically you want this. You have a two variable functions like the heat equation, but you are assuming that there is a g of x such that this is true. Okay, then the function, this is the conclusion. Derivative with respect to time of the integral of f of xt the mu equals the integral of derivative with respect to time of f of xt the mu. So that's the conclusion. We can interchange derivative with integral. That's basically the statement. Okay.
When we talk to unimperfect function, you have the function is going from the capital X.
This one?
Yes.
No, that's a small x. So it's just saying you fix t sub 0, and then it's just saying fix the t sub 0. So if you fix t sub 0, then you have a function that depends only on x. So that's just notation, but that's good to expose you to that notation. So that means you have two variable functions, and if you fix t, so let's say t0 is 1000. So x to f of x 1000 is just a function of x. It's not a function of t sub 0. So he's saying that each time that you fix t, you have an integrable function with respect to x. That's what it's saying. So we want to interchange the integral with the derivative with respect to time. But you see, probably is more understanding if I say that this is dx. Okay, so I have an integral with respect to x. So and I find the derivative with respect to time. So I can interchange the derivative with respect to time with the integral with respect to x. Okay. But usually, since it's general, this theorems that we have been proven are so powerful that this is true for general measure. Okay, so this is true for general measure. So I just put R for understanding, but this one can be X, any space X, okay, with a measure. But if you want a particular case, just choose the Lebesgue measure, and then there will be X. So you intercept the derivative with respect to X with integral with respect to X with derivative with respect to time. Okay. So here is the proof. So you'll see it's kind of short. So let's use the notation. So proof. So let's use the notation. So I don't have to write all the time integrals. So f of t, capital F of t equals the integral of f of xt, the mu of x. Okay. So in particular, with this notation, that means the derivative of capital F with respect to time is just this. Okay. So I just defining the capital F like that. So I save on time with my notation. Okay. So so let t be any point of AB. Okay. So basically your time is between A and B. And let t sub n converging to t with t n different of t. So remember, we want to talk about derivative, right? So then I can write the derivative of f with respect to time of the form limit of t sub n goes to t of f of x t sub n minus f of x t sub n minus t, and x belongs to x. Okay, so that's just definition. I haven't done anything weird, right? So now this is measurable because I make that assumption. Remember, it's integrable. So the difference is measurable, and I divide it by constant, so all the whole thing is measurable. So the function, that's a way to describe the function. X, to each point, I assign the derivative with respect to time is measurable. Because each time that I take the integral of a function, I need to make sure that function is measurable. Okay? Otherwise, this theory cannot be applied. Okay? So this is just kind of making sure that everything is correct. So now we start with the proof. So really, the proof, if you think about it, the main ingredients you will have to identify them, but then you have to write all these little details just to make sure it's correct. So this is the proof. If x belongs to x and t sub n belongs to AB, we have f of x t sub n minus f of x t over t sub n minus t, and we can say that this is equal to the derivative with respect to of f with respect to time of x for some point s1, and s1 is between t sub n and t. So why is this true? What theorem I'm using? Why is that true? S1 is a point between t sub n and t. So what is? So I'm writing this. This difference and this quotient as the derivative at a point. So that was one of the theorems of calculus that you learned in analysis 1. That's similar. The mean value theorem. This is true by mean value theorem. So I'm going to explain it to you just like I explained to my calculus students. So so forget about x. X is fixed, you see. So this is just a function where t sub n and t are changing. So suppose this is t sub n and this is t, okay, and your function is something like this. This is f, and usually you put point t. Okay, point means you fix the x. So you fix the x, you just have this one-dimensional function. So fx t sub n, right? So fx t sub n is this point, fxt is this point. What is fxtn minus fxt over tn minus t? What does represent? Slope of what? Not the tangent. Huh? No. But they're close. What else can you have 2 points.
So we have y difference, delta y on that.
Is the slope of what? Of the secant line connecting these 2 points. Okay, and then the theorem is saying that there is an S1 here such that the slope of the tangent line is the same. Okay, so that's mean value theorem. So you believe that, right? Okay, so by mean value theorem you have that, and therefore we take absolute values everywhere. So we take absolute value f of x t sub n minus f of x t sub 0 over t sub n minus t sub 0 absolute value, and this is equal to the partial derivative of f with respect to t of x s1, And then by hypothesis, all these guys are less or equal than g of x, right? For some g of x, right? That was one of my hypothesis. Well, I couldn't find it, but this was less or equal than g of x. So that's good, because then I'm gonna take, I can do the following. I'm gonna take the integral of these guys. I'm gonna take the integral of fx t sub n minus fxt over t sub n minus t, the mu of x. Okay, and then you can write this just for notation, just to make it nicer and easier to explain. You can write this like the integral of f of x t sub n dx minus the integral of f of xt, the mu dx divided by t sub n minus t. Okay, so I just using my properties of integration, but then by definition I just said what is this guy? This is capital F of what? This is capital F of t sub n. That was my definition. And then this is my definition of capital F of t. And then I have t sub n minus t. Okay? So I just want to say that, f t sub n minus f of t sub n minus t is exactly that this guy. So now we are going to be able to see it. So because, sometimes you don't recognize things if they are in a complicated way. But once you write it in a familiar way, because this is familiar, this is just calculus 1. So let's take the limit. So taking the limit on both sides, so we take limit outside, so we'll get the following. We'll get limit of f t sub n minus f of t sub n minus t sub n goes to t, right? And this is, what is the definition of this? Limit of capital F t sub n minus capital F t over t sub n minus t. What is that? When t sub n goes to t. From calculus 1. So ft sub n, what is the derivative? What is this? That's the derivative of f with respect to t, okay, of t. Okay, that's just calculus 1, right? Definition. But then I took, but also for from here, sorry, this is moving too much, sorry. I'm gonna have to use this one here. By this definition, this guy equals to that guy. So I take my limit outside, t sub n goes to t, and then I have the integral of f of x t sub n minus f of x t over t sub n minus t the mu of x. But just as by dominated convergence theorem, right? Because this guy satisfies dominated convergence theorem. Remember, I said this dominated by 0 x. I can put my limit inside of this guy. You can take this, and when you take this limit, you got, what do you got? Integral of the mu of x of who? What is the definition of this one? So you have x, tn, x is fixed, but you have tn goes to t, so this is gonna be the derivative of f with respect to time of xt. So in conclusion, you have the derivative inside of f, but remember, this guy was, by definition, that was derivative with respect to time of the integral of f of xt, the mu of x. So that's the definition of capital F, right? Is the integral of f of xt, the mu of x. And I have the derivative of capital F. So the derivative of capital F is, but also capital F is the integral of xt mu x. So all these concludes that these two are equal. So in conclusion, I have the derivative with respect to time, integral of f of xt, the mu of x, as I want. So I can interchange derivative with integral. Okay, and that's the conclusion of the proof. So questions? So you see, everything is clear thanks to the, of course, you know, you just have to read it again. Sometimes you feel like, you know, there was a little thing that you didn't get, but this is, you'll take a look, and this is a very, very standard proof of this theme. Okay, and the last theorem of the semester. So so the last thing of the semester is connecting this Lebesgue integral with your Riemann integral. So I'm going to prove that the Riemann integral and the Lebesgue integral are the same in closed intervals. So all the properties that you learn, like integration by parts, trigonometric substitution, all that is the same on the real line. So that's great, because then when it's convenient for you to do normal integration from calculus 2, but when you need to interchange limits, when you want to interchange derivative, then you can do it because you know Lebesgue integral. You just need to check that your function satisfies the properties. Okay, so this is the theorem. So theorem. So a Riemann integrable function on AB, on the interval AB, is Lebesgue integrable and the integrals are equal. So well, basically we're saying is, you know, you have your Riemann integral ab of f of x dx, and then you compare it with the Lebesgue integral f, and then you put this ab d lambda, so they are the same. So in other words, the Riemann integral is the same that the integral of Lebesgue integral restricted to of the function restricted to AB. Okay. So yeah. So patients asked me about these questions. So so let me. Do you guys understand this notation? So this notation means, for example, I have my function, or my function, I have my function f of x. Let's say this is my function f of x. But then I wanna grab my function f of x times 0 to infinity. Okay. So what it means is that my new function, instead of getting all that function, means my function is gonna be, this part is gonna be 0, but this part stays alive from 0 to infinity. So this part, that's my new function. This is my function. Okay, that's what it means. It's just cut whatever that you don't need. So that means I cut from 0 to infinity, but I could make another cut. I could say f between -1 and 1. So that would mean that I got this function and I just consider between -1 and 1. Let's say this is -1 and this is 1. So I just consider this function between -1 and 1, and everything else is gonna be 0. So this is 0. Okay, so that's what it means, that notation. Okay, so let's do the proof. So proof, so suppose you have an integrable function. So for being a Riemann integrable function, you need the function to be bounded and continuous, or continuous except for a finite number of points. So a typical function integrable between a and b could be something like, you know, I'm gonna make exactly the same that I used for my theorem of Lebesgue integral. So something like this. Okay, remember I used this one to prove that I said that was really important proof. So this is f of x is bounded and is continuous, so it's Riemann integrable. Okay, so if it's not bounded, then it's not integrable, because the integral is going to be infinity. However, in Lebesgue measure, you can have integrals equal to infinity. So let f be a Riemann integrable function vanishing outside of AB, and let f less than m. So that means B is bounded, you know. So the function is bounded because this is m, this is m, so the function doesn't cross m. Okay, so for some constant m. No, so when you use epsilon, you mean the function is really small. No, this is just is bounded, can be 1,000, a million. When you use epsilon, you wanna say epsilon can be 0.00001. Okay. It's bounded, but you know, usually this m can be, m is usually a big number. Epsilon is usually a small number. So now we're gonna do a partition. Let n. So remember that the Riemann integral, it has this concept of left hand sum, right hand sum, you know, that kind of stuff. We're gonna do something similar, not exactly, but that's what we're gonna do. We're gonna take the inf and the sup of the intervals, and then we're gonna say that the limit of both is gonna be the same, and in the middle is gonna be the Lebesgue integral. So that's what we're gonna do. So let n belongs to the natural number. Let's partition the interval. AB, so let's put it open, into n intervals of equal length. So just like in calculus 1, so we are gonna take delta x equals b minus a over n. Okay, so we are gonna consider the following intervals. So we're gonna get from a to yeah.
One side zero and one side.
It doesn't matter. It's a point. It's just to say that you don't include the b. So you
In that case, it would not be Riemann integral.
no, because Riemann integral you can take a point out. It doesn't matter. Because a Riemann integral you can remember that a Riemann integral can have finite discontinuities. So you could have this one, could hit this one, or this is closed, this is closed, this is open, and then the integral is gonna be the same in Riemann integral, because you will split like from here to here plus from here to here plus from here to here. It doesn't. So I mean, you can just put it. You can put it b like that, but technically it's wrong because you are not including the b at the end. So let me show you why. So it's technical. It's not really important. So this is my first interval is this one. My next interval is a plus delta x, a plus 2 delta x. Then my next interval, so I taking like close, open, close, open. So in that way I finish open on B. Okay. So then is and then we got to take it. The last one is gonna be a plus n minus 1 delta x, a plus n delta x. So you see I didn't include b at the end. So basically what I'm doing, here. So what I'm doing here is dividing just like I do in calculus 1. Same size. Okay, same size. Not a Lebesgue integral, remember? Because in Lebesgue integral we divide here. Remember? And then I start taking the inverse images. So that was different. So that's the different approach. Then I'm doing Riemann. So I'm dividing like this, and then I'm gonna define my first approximation. Then we define the functions. G sub n of x equals the inf of the f of x, where x belongs to the corresponding n interval. But you know, this is notation, so it's not to a plus k minus 1 delta x comma a plus k delta x. So I'm taking the inf of this guy 0 otherwise. Okay, so what I'm doing, so let me make a bigger graph so I can, so it's sure you understand that. This is my function. So I'm going to choose this one. Okay, so this is A, this is B. Will he be? It doesn't have to be like that. I just want it to be symmetric so you can compare it with the Lebesgue integral when we did it. So so I divided on intervals 1, 2, 3, 4, 5 and 6, let's say. Okay, so I'm gonna take the inf of the images from A to B, right? So what is this, the smallest one? So the smallest of this interval is 0, right? So this is my first. I cannot write it twice. Let me see if I can recover. Oh, I recovered. Good. So let me use a really, I don't know if I can use a bigger one, like that. But then for the next interval from here to here, I choose the smallest one. So the smallest one of all these guys is this one. So goes like that, right? That's the inf, right? Now I go here, from here to here, my inf is gonna be this guy, so it's go here. Now I go from here to here, the inf is gonna be this guy. But now you see my function is becoming decreasing. So my inf between here and here, between this point and this point, so my inf is this guy. So now this is my inf. So it changes. And then my inf from here to here is gonna be this one. That's my approximation. So I'm approximating, when I find the integral, I'm gonna approximate as this. Oh, my eraser is kind of broken. gonna be like this. Supposedly something like that, right? And then let's say it's like that. Okay, so this is gonna be my approximation with the IMPs. Okay, but the smaller I get my intervals, the better approximation I have for my interval, right? So yeah, so now, so what I observe, I call this one GNN. So now, whatever I observe with this, that since G sub n is bounded, right? Why? Because f of x is bounded. So G sub n is bounded. So now we are talking Gn, G1, G2, G3, G4 are not decreasing. Right? Because the smallest intervals I get, the bigger my G sub n is, right? So if I have G1000 means I had 1000 intervals. So my area is gonna be bigger. So this is bounded, no decrease. My area is bigger and bigger and bigger. Since G sub n is no bounded, no decreasing sequence of functions, it converges to every x belongs to R. So that means what I'm saying is the limit of g of nx when n goes to infinity exists. Because for each x I have a bounded sequence of, no, it's a bounded increasing sequence. So by real analysis 1, for each x, the limit exists. So for each x, I can define the limit, and let's call it g of x. For each x. So I'm not going to have g of x equals to infinity, because this is the same. Remember this important thing we had used before. An increasing sequence that is bounded has a limit. Okay, so that's my for g of n of x. Oh no, this is just, let's say this, the blue one is just 1, 2, 3, 4, 5, 6. This is G6. Oh, just the lines. The lines.
They are all equal, right?
Huh? Second?
They are all equal, right? We divide into the
What do you mean that they're equal? What is equal?
partitions.
The partitions are equal.
So if they are G, then G2, they are equal.
No, because this is G6. Now do G7 or G9. To do G9 of x, instead of doing 6 times, you do it. Wow, what happened?